Good afternoon. I'm Jill Pfeiffer, and it's my great pleasure and honor in my role as president of AMS to introduce the distinguished speaker of this lecture. Ken Ribet, professor of mathematics at UC Berkeley, served as president of AMS from 2017 to 2019 and is giving this invited address from a past president on a subject, Fermat's last theorem, that has inspired mathematicians for, well, centuries. Research on Fermat's last theorem resulted in mathematical ideas that have transformed the field, a body of work to which Ken Ribet has made fundamental and exciting contributions. Over the decades of his career, his research in number theory has earned him extraordinary honors. Some of these include the Fermat Prize in 1989, elected membership in the American Academy of Arts and Sciences and in the U.S. National Academy of Sciences, an honorary doctorate from Brown University in 1998, his undergraduate alma mater. I also want to share with you that Ken has been widely recognized in the mathematical community for his talent for and love of teaching and for his mentorship of students, more than 24 PhD students by now. Ken has been involved in AMS service and governance for many years, and he's contributed quite a bit, but let me just point out one of his signature contributions as president, namely his leadership for the Campaign for the Next Generation, co-chaired with Jen Tabak and Rob Lazarsfeld. Ken reached out to members, to the leadership of the society, identified donors, and helped to create the campaign committee. He was truly the outward face of this tremendously successful fundraising campaign for interests, the next generation, which are close to his heart. As a direct result of Ken's and others' efforts, AMS now has a $3 million and growing endowment to permanently give small but impactful grants to early career mathematicians. So please join me in welcoming Ken Ribet.
And I want to thank you, so many of you, for coming out to what will prove to be a very technical discussion of advanced number theory. I'm glad that management directed you to the emergency exits in case they're useful. I am going to talk about Fermat's last theorem, and it's really impossible to talk about that subject without starting with Fermat's equation, so we know what the theorem says. It says that when you consider non-zero integers, or if you prefer positive integers, and you take perfect nth powers, you can't get two perfect nth powers to add up to a third nth power for n bigger than 2, for n greater than or equal to 3. And when I give general talks on Fermat's last theorem, as I did quite recently at Brown University, where I was introduced by Jill Pfeiffer, I point out that it's possible to have two perfect squares sum up to be a third perfect square. 9 plus 16 is 25, and the theorem says that you really stop at perfect squares. So this theorem was apparently stated, probably stated, in a marginal note that Pierre de Fermat wrote in his copy of Diophantus sometime in the 17th century. And it's probably a fair statement to say that he wrote this marginal note about 375 years ago. We don't have the actual marginal note because his copy, which passed into the hands of his son Samuel de Fermat, cannot be found. We generally believe that Fermat, as a mature mathematician, no longer believed that he had proved the statement, which has become known as his theorem, but it's not his theorem. He spent a considerable amount of time using his method of infinite descent, which basically means mathematical induction, to talk about a special case of the theorem. He proved, for example, that the sum of two perfect fourth powers cannot be a perfect square, and therefore, in particular, cannot be a perfect fourth power. And because of that, and the fact that the theorem for given n implies the same statement for any multiples of n as exponent, if you think about the factorization of positive integers n, you realize that powers of 2 are ruled out, and numbers bigger than 2 will then be divisible, if they're not powers of 2, by a prime number bigger than or equal to 3. So Fermat's work reduced the theorem to the case x to the n plus y to the n equals z to the n, where n is a prime number that we might as well call p, and p can be 3 or more. But then in the next century, Euler wrote down an argument for n equal 3, and he did that by factoring equations in what we now say is the ring of integers of the field of third roots of unity, what you get by adjoining -1 plus the square root of -3 over 2. And the fact that he did that certainly reduced the theorem to the case of a prime number bigger than or equal to 5. And not only that, it kind of set the tone for further work on Fermat's last theorem for the next 250 years, where people basically developed, as needed, the modern theory of factorization in algebraic number rings. So Fermat's last theorem not only was a very old problem when it was finally settled in the 1990s, but it had been a tremendously fruitful problem where people had developed new techniques in mathematics as they attempted to solve it. And I hope you can see to the bottom of the slides. It looks like you can. This problem was open until the 1990s, but I did just allude to the fact that it was settled in the 1990s. It was settled in 1994. And the name that's associated with the resolution of Fermat's last theorem, the single name, is that of Andrew Wiles, who's now a professor at Oxford. He was then a professor at Princeton. And he announced his proof at a workshop in June 1993 that was at the Isaac Newton Institute in Cambridge, England. I was present at that workshop. And you probably can't see the small writing on the slide, but this is a scan of the original program that I found in my office last week. And what's remarkable is that on the first 3 days of this workshop, Andrew gave the morning lecture, the first lecture. So he gave 3 lectures in a workshop where typically people would just give 1 lecture and then cede the stage to somebody else. And he announced the resolution of Fermat's last theorem on Wednesday, June 23. I'm looking down at my slides. His lecture was between 10 and 11 in the morning. And then, unfortunately, after his lecture, I had to give the next lecture in the workshop, which was it was a hard act to follow. One thing that happened during the period between the 2 lectures is that I spoke on the phone to Gina Colada, who wrote up the story for the New York Times. I was hiding under a desk because it was so noisy out in the corridor. And the next morning in the New York Times, there was a front page article on Fermat's last theorem that mentioned the names of the people who had been associated with the proof and basically said, everything is over. We've now proved Fermat's last theorem. There was, by the way, these slides are punctuated by photos that I took of various people who figure in the story. This is a photo that I took in Norway when we were at an Abel symposium in June 2002, and that's Andrew Wiles in the setting sun. Now, after the announcement that Fermat's last theorem had been solved, which was in June 1993, there were several of us who were asked to be referees of the manuscript that was not public, but it was given to 5 or 6 different people. And one of the readers was Nick Katz, our friend from Princeton, who sent lots of email messages and faxes to Andrew because Nick was in the US and Andrew was in Princeton, it was in Europe. And each time that Nick had a question, he got an instant answer. And then there was one question where there was no answer. And Nick had actually found a gap in the manuscript and the proof that it took people a really long time to realize was a significant problem. So for the immediate time after the announcement in July and August and September, many of us were doing interviews and telling people what a great result this was. But in fact, there has been a problem that was kind of festering, and it took a while before the mathematical community realized that the proof was not complete. And the situation remained apparently static for pretty much a year. And then in the early fall of 1994, Richard Taylor, who had been Andrew Wiles' thesis student before this had started, worked with Andrew, and together they put together a new manuscript with some new techniques that did exactly what the original manuscript failed to do at one particular juncture. And so by October 1994, it was clear that the gap had been filled and the proof had been completed. And then there was a new wave of jubilation, and this time it really stuck. What I'm going to do now is, in a couple of bullet points or Roman numerals, just kind of say what the outline of the proof was with the results of Wiles and Taylor-Wiles together. And then I will give you lots more information about the elements of the proof. So I'm trying to sketch out some skeletal proof and then fill in some of the details. So the first thing is that you do it by contradiction. So you suppose that Fermat's last theorem is false. That means there are integers, a, b, and c, none of them 0, where a to the b plus b to the p is equal to c to the p. And you can and do assume that p is at least 5. And then what you'd like to do is derive a contradiction from that. And there's a little technical point, which is that you can shuffle around the order of A, B, and C and change some of the signs so that the statements that I'm about to make are actually literally true, and I'm not stretching the truth all that much. But the major construction, which is the one displayed equation on the slide, is that you start with A, B, and you don't even need C, because C is defined implicitly in terms of A and B. And you construct some auxiliary object, which is a new cubic equation. And this equation is an elliptic curve. An elliptic curve is just a plane curve defined by a single cubic equation, if you like. And this is called a Frey elliptic curve. So in a minute, I'll tell you about Gerhard Frey. Frey was the person who suggested making this construction and said that he thought that it could lead to an ultimate proof of Fermat's last theorem. And it turns out that you don't really need to kind of think about A, B, and C as integers exactly from that point of view. What you do is you think about this elliptic curve and you derive its properties and you discover the two of them are opposite from each other. You get a contradiction. So that's the way the proof went. And the main point about the contradiction, so what's special about this particular cubic equation? Well, if you look at the right-hand side, you have a cubic polynomial. And if you remember how to compute the discriminant of a cubic polynomial, you take the product of the three differences among the roots, and then you square the result. And if you look at the roots are 0, a to the p, and minus b to the p. And the difference between minus a to the p and b to the p up to sine is c to the p. And so the up to sine, the polynomial has a discriminant which is a, b, c, all to the power 2p, and it's a perfect pth power. So this is very unusual. P is, in your mind, I said it's at least 5, but think that it's, at least 100 million or something. Because by the time this was all announced using various criteria, starting with Kummer's criterion from the 19th century, people doing computer calculations had verified that Fermat's last theorem was true up to exponent, into the millions. And so the numbers involved are presumably very, very big, although in the end you prove they don't exist at all. It's kind of a funny thing to talk about. But nonetheless, you have this amazing cubic polynomial whose discriminant is a very high power, and a pth power in particular. And then there was a kind of a race to prove that this elliptic curve is not what's called modular. And what does it mean to be modular? Well, I'm going to tell you that in a few minutes. And the idea of how to prove it was not modular was set out in some manuscript, actually a letter that was written down by Jean-Pierre Serre. And this was a very public letter. People made Xerox copies. There was no internet yet, really. And everyone understood that you had to prove a certain property of this elliptic curve in order to check that it wasn't modular. And the work that I did on Fermat's last theorem was to show that this property was correct. So I proved basically in 1986, although my manuscript didn't get published for several years, that E is not modular. So modular is a single buzzword meaning associated with modular forms. And the contradiction is that in 1993 and then 1994, Wiles, together with this Taylor-Wiles new manuscript, proved that the elliptic curve is modular. So it's both non-modular and modular, and that's the contradiction. And in fact, when Wiles and Taylor-Wiles worked, they didn't work with that particular elliptic curve. They worked with a very wide class of elliptic curves called semi-stable elliptic curves, and they proved that all semi-stable elliptic curves over the field of rational numbers are modular. And what I said a few minutes ago about shuffling around A, B, and C and changing signs was exactly to make it true that the resulting elliptic curve was semi-stable, and that's the category that Wiles started working with in the late 1980s. And if you have kept track of all these Roman numerals, you'll see that we have a contradiction. Well, I really just told you that. The thing is both modular and non-modular, and therefore the game is over. There was no elliptic curve. So before defining terms, I'll show you Frey. Here's Gerhard Frey, and someone you may recognize as the person standing in front of you. This is from June 2016, 3.5 years ago, at a conference at the Fields Institute in Toronto. And now we go back and talk about the basic objects in my skeletal outline. First of all, there's this idea of an elliptic curve. So elliptic curves are kind of fundamental in lots of areas of mathematics and outside of mathematics, including physics and I'm not sure what else. They're used very widely in cryptography in different ways, and they are given simply by a single equation, in most cases, y squared equals a cubic in x. And you saw an example of that where the cubic was this funny cubic with a very smooth, as one says, discriminant, but it could be anything. You know, it could be y squared equals x cubed plus x plus 1 or something like that. And the main thing that you want is that the cubic should have a non-zero discriminant. That's what makes the elliptic curve a non-singular curve in the sense that you don't have simultaneous vanishing of partial derivatives at any point on the curve. And an elliptic curve is given by such an equation, and technically it's the curve defined by that equation together with a single point on the curve, which can be taken to be the unique point at infinity. So when you write y squared equals f of x, you're defining a curve in the affine plane, but in algebraic geometry, it's much better in most cases to work with projective space instead of affine space. And if you look at this type of equation in the projective plane, there's a single point on it that is not on the affine plane. That's called a point at infinity, and that's the distinguished point that completes the definition of the elliptic curve. The elliptic curve is the curve defined by this equation plus this point at infinity. And we already saw one example, but here's a picture of another, y squared equals x cubed minus x plus 1. And it's probably big enough that most of you can see that there are 6 points that are darkened in on the screen. One of them is gold, and the other 5 are blue. That's because at Berkeley, the colors of the golden bears are blue and gold. And the gold point is one of 2 points with a special property that I'll describe in a minute. But there are other points that aren't darkened. For example, 0, 1, and 0 minus 1. I'm not sure why I didn't darken them. And it's actually quite remarkable. I wrote down this curve pretty much at random. although I knew that the discriminant of the right-hand side had a very small absolute value, namely the discriminant is minus 23, and it turns out that this particular elliptic curve has a remarkable number of integer points. There are 12 of them, and you can see on the screen, for example, 3 plus or minus 5, and then off the screen there are 4 points, 2 of them with x-coordinate 5 and 2 of them with x-coordinate 56. Mostly, if you look at examples of elliptic curves, you'll see a fair number of points with rational coordinates, but the denominators are typically quite big. And this is a nice example because the denominators are 1 in some points that you can draw. And one of the things that you can do with an elliptic curve is you can take the equation for the elliptic curve, which is a literal equation, you know, something equals something, and you can regard it as a congruence modulo different prime numbers, 2, 3, 5, 7, 5, whatever, 11. And every time you do that, you get a curve, and for the most part, the curve will have a non-zero discriminant, although in the example that I just gave, if you look at the thing as a congruence mod 23, the discriminant all of a sudden will become 0, and then you don't get an elliptic curve mod 23, but you do get an elliptic curve mod 3, 5, 7, 11, and all but finitely many primes. And when you do get an elliptic curve, you have what's called good reduction. Otherwise, you have bad reduction. And this particular example that I gave you with y squared equals x cubed minus x plus 1 has good reduction except at 2 and 23. 2 is problematic for it, it turns out, and 23 is problematic for the reason that I just said, namely the discriminant is minus 23. And then when you reduce this curve, you can start doing finite things because you get a curve over a ring with just a finite number of elements, the integers mod 3 or 5 or 7. But before I tell you about that, which is the key to explaining what modular means, I'll make an attempt of telling you in some sense what semi-stable means. When you have bad reduction, there are 2 kinds. There's additive and multiplicative. And a curve is semi-stable if none of the reductions happens to be additive. So every reduction is either good reduction or multiplicative reduction. And in the example that I just gave, the reduction at 23 is multiplicative and the reduction at 2 is additive. So the particular elliptic curve that I give you as my running example is actually not a semi-stable elliptic curve. And there's a numerical quantity that goes along with this. It's called the conductor of an elliptic curve. I should have said numerical invariant. And the conductor is divisible by exactly the primes at which the reduction is bad. And it's divisible to the first power when the reduction is multiplicative, and to a higher power, typically only the second power, if the reduction is additive. And so, for example, this elliptic curve has conductor 96, 4 times 23. Another way to say that an elliptic curve is semi-stable is to say that its conductor is square free. Okay? So that's some of the vocabulary. And to describe modularity, now I just have to tell you about this finite situation that you get when you take the original equation and you regard it as a congruence. If you regard the thing as a congruence, then you're in a situation where the ring is the ring of integers mod L, which has only L elements, 0, 1, 2, 3, up to L minus 1. And if you look at the pairs, x and y, there are only L possibilities for x and L possibilities for y, so there are L squared possibilities for the pair. And then there's the point at infinity, so this elliptic curve could have, at most, L squared plus 1 points. And if you think about another curve over what we call the field with L elements, that just means the integers mod L, you could just have the projective line. And the points of the projective line are 0, 1, 2, 3, up to L minus 1, that's L points, together with a point at infinity, so you get to L plus 1. And when you take the difference between the L plus 1 and the number of points that this elliptic curve happens to have, you get a number that we think of as an error term, and that's because of a theorem of Hasse that tells you that it has small absolute value, basically the square root of L, whereas we're comparing two numbers of higher order, numbers that are roughly L or L plus 1. And this error term is negative when the elliptic curve has lots of points, and it's positive when the elliptic curve has relatively few points. And then what you do, you kind of keep book on these error terms. You get an error term for every prime of good reduction. So in the case of the example, for 3, 5, 7, 11, 13, 17, 19, you don't want to take 23 because that's bad, but then you go to 29 and so on. You have this infinite list of numbers, and the modularity means that this infinite list appears somewhere in the appropriate book, in the sense of proofs from the book. It's the book of modular forms. And modular form is you can think of as a power series. I say it's a Fourier series. It's given in powers of a variable that's typically written Q, and Q in the subject is an abbreviation for e to the 2 pi I tau or z, where the tau or z is a variable in the complex upper half plane, complex numbers with positive imaginary part. And the modular form that is associated with this elliptic curve starts as indicated on the screen. And for example, if you look at the coefficient of q to the 7, that's a negative coefficient. That means the elliptic curve has lots of points. It has more than 8 points. And how many more than 8? Well, 4 more than 8, so it has 12 points modulo 7. And this is not too surprising in a certain sense, because the elliptic curve had already quite a few points with integer coordinates. Of course, these points with integer coordinates could collapse mod 7. 2 of them could be the same as 2 others. For example, there was a 56 on some previous slide, and modulo 7, 56 is the same as 0. But then you can get other points that weren't the reduction of integer points, and 12 is a kind of reasonable number for a curve like that to have mod 7. I'm just trying to tell you that the numerics are not super surprising. And what happened in 1994, as I already said when I had those Roman numerals up on the screen, is that Wiles plus Taylor-Wiles, the package of the 2 articles that they wrote, prove that all elliptic curves with square free conductor over the rational field were modular. They were associated with a modular form. And then there was a little kind of revisionary period between 1994 and the summer of 1995, where a number of different authors in different articles expanded the range of modularity. And by July, I think it was, of 1999, this group had proved that all elliptic curves, semi-stable or not, over the rational field are associated to modular forms. And the names associated with this work between 1994, in addition to Richard Taylor, is Christoph Breuil, Brian Conrad, and Fred Diamond. And the work modulo 3 turned out to be the stumbling block in the last article in the series. So they really proved modularity. And now I want to go back to elliptic curves and tell you a little bit more about the structure or properties of elliptic curves, so that I can make sense of parts of the method that intervene when you prove modularity. So the biggest thing is that an elliptic curve is a group. If you have 2 points on the elliptic curve, you can make a third. And the basic idea, which is seen only in small type, so to speak, on the slide, but a lot bigger on the next slide, is that if you have a cubic curve and you have a line, and you intersect the line and the curve, that line will intersect, in general, 3 points of the curve. And if 2 of the points have rational coordinates, then the third will also have rational coordinates, because it's some business where the sum of 3 roots of a cubic is one of the coefficients of the cubic, and we're dealing only with equations with rational coordinates. It's not true in general that the sum, that if you start with 2 integer points, you get a third integer point, but it is true with rational points. And the formulas for how to add 2 points involve denominators, and you can find these formulas, for example, in Joe Silverman's book on the arithmetic of elliptic curves. And so here, what happens, well, let me spill the beans here. The set of rational points of this elliptic curve happens to form an infinite cyclic group, and this infinite cyclic group has 2 generators, like all infinite cyclic groups. And one of the generators is the point P with gold, and the other generator will then be minus P, which is below it. And one thing to understand is that negation in this situation means reflection through the x-axis. And the other thing is that when you take 2 points and you find the third point using this business with a straight line, the third point is not the sum of the 2 points, but it works out to be the negative of the sum of the 2 points. And so, for example, if we were to take this point P and try to add it to itself, that would mean that we kind of take the tangent line at P, and then the third counting multiplicity point that the tangent line would strike on the elliptic curve would be the point -1 comma -1. So then 2 times P is not -1 -1, but it's the reflection of that through the x-axis, which is -1 comma 1. And so on, if you go 2 to the left of the point P, that's actually twice P. And if you fool around with this construction, which is called the chord and tangent construction, we just had a tangent, and when you connect 2 distinct points, that's the chord, you will see that the lowest point that's marked 4P really is the sum of 2P in itself, or you can add P plus P and then continue that, have 3 additions, and you get to the 4P. So the main point, which is now written in words on the previous slide, but I just said it, is that summing to 0, and 0 is the point at infinity. If you want to have a group, you have to say what the 0 element of the group is, and the best way to start is to take the one point that you know, namely the point at infinity, and then with that convention, 3 points sum to the point at infinity if and only if they're collinear. So this elliptic curve is a group, and you can have a group of rational points, you can have the group of real points, you could have the group of complex points, and you could have the group of points modulo 7, 11, 17, or 29, whatever you like. So this is a completely algebraic construction that enables you to add on the curve. And now here is something that is kind of technical, which is that you take a positive integer n. In our discussion, n might be 3, or it might be the prime in the exponent of Fermat's last theorem, and you look at the set of points on the curve with complex or algebraic coordinates, it doesn't matter, such that n times the point is the origin. And you say, what is that? Well, that's an abelian group. You're solving some equations. You can see fairly easily there are only a finite number of solutions because you're just solving some polynomials of known degree. And it turns out that you can visualize this group very well if you remember Weierstrass theory from the back of Alfors's book, where an elliptic curve can be written as the complex plane modulo a lattice. And then this group that I'm describing is just 1 over n times the lattice, a slightly dilated lattice, modulo the lattice. And the lattice is just a free abelian group of rank 2, and what you get when you make this construction is something of rank 2 over the set of integers modulo n. And so the thing is kind of very, very concrete, and if you want to understand what these points are in a specific example, you can do that. You can use software like Sage, which was founded by William Stein, who I wanted to mention at some point in this talk, because a lot of the concrete work that people do in the subject really comes from the tools that he introduced. So the first bullet point is just that it doesn't matter whether you use Q bar or C, and that's because you're just solving algebraic equations with rational coefficients. And the second thing is that you get something that's free of rank 2 over the cyclic group with n elements, the group of integers mod n. So that you can see by Weierstrass theory. And the thing that's kind of really fundamental in the subject is that because you're solving equations with rational coefficients, what happens is whatever you get as the solutions are permuted amongst themselves by the Galois group of the rational field. And so the Galois group of the rational field kind of permutes the set of n squared elements, but it permutes it in such a way that you respect the addition on this group E of n, because the addition involves writing down equations whose coefficients are rational numbers, and they won't be disturbed by the Galois group. And so instead of getting, some huge extension whose Galois group might be, the symmetric group on n squared elements, instead you get a Galois extension whose Galois group is just a group of matrices, because what you're doing is you're taking automorphisms of something free over the cyclic group of order n. And so you get 2 by 2 invertible matrices modulo n. So what you get is called a representation, because a representation of a group is a homomorphism from the group into a group of matrices. This is called a Galois representation because you have a Galois group. And in particular, you can take the example of a Frey curve that was introduced by imagining that there is some solution to Fermat's equation, and you can take E of n where n is equal to p, and then you get a Galois representation mod p, which is kind of mapping into 2 by 2 matrices, invertible matrices, modulo p. And you can ask whether or not in some basis this representation is upper triangular. Then the representation would be called reducible. And it turns out there's a really hard theorem of Barry-Mazur from 1977 that in fact this representation is irreducible. It cannot be made upper triangular. And this has nothing to do, by the way, with the particular example. It's true anytime you have an elliptic curve over the rational numbers that is given by y squared equals a polynomial with rational roots, like this one has, factored cubic. Mazur proved that you cannot get some subgroup stable by Galois of order p. And this is true for any p bigger than or equal to 5. And it's certainly, kind of even more true if p is gigantic, like 3 million, as you imagine the situation to be when you're talking about Fermat. And I don't want to kind of get stuck on technicalities, but the point is that this elliptic curve, if you have the theorem of Wiles and Mazur-Wiles, Taylor-Wiles, is actually modular. It's associated with a modular form, and you can transpose that information to the situation where you just think about the Galois representation. The Galois representation is also going to be associated to a modular form, and the association is very simple. It's that when you look at distinguished elements in the Galois group associated to random prime numbers, Frobenius elements, and you look at the matrices that you get, the traces of those matrices should be given by the coefficients of the modular form, of course, looked at only modulo p, because this is a representation modulo p. And the whole point is that this elliptic curve has a conductor, which is probably immense, because the numbers a, b, and c are immense. And therefore, you might imagine that the representation, well, it has some conductor that you can define. You might imagine that this conductor is also gigantic. But what happens is that because the polynomial defining the Frey curve has this discriminant that's a pth power, the conductor of this particular representation is minuscule. It's just the number 2. And there is a conjecture that Serre wrote down in 1987 to clarify things, although it really grew out of correspondence that he had with John Tate long before, where he said, if you have a representation that has some minimal looking properties, as this one does, it should be associated with a modular form. And the modular form that is associated with a representation with conductor 2 should be a modular form of level 2. And the whole point to Serre is that there are no modular forms of level 2, and the whole contradiction can somehow be channeled into looking at this representation. And so Serre's challenge, which he wrote down before he really published this article, but kind of roughly at the same time, was somehow trying to take an elliptic curve with huge conductor and therefore associating to it a modular form with very large level. I'm not sure that I said what the level was. I probably removed the relevant slide, but it tells you what subgroup of SL2Z you have to look at. Large level means a very small subgroup. What Serre said is you should take this thing and there should be some method of somehow parlaying this modular form of very high conductor into a modular form of conductor 2. And that's what I did using my interests in Galois theory and modular forms. I thought that I would somehow take a tiny break from the technicalities by telling you about two of my interests that I found Facebook knew about me. It says that modular form is a local business for some reason. And what I proved, my contribution to the whole thing in the mid-1980s, was to show that if you knew that rho came from a modular form of very high level and it had this very small conductor, then you could somehow whittle away at the conductor incrementally and get down to a conductor 2 and get the contradiction that way. And what I did, this idea of moving from high level to low level, of course, is called level lowering, and sometimes it's called level adjustment. And now, just to kind of summarize the situation 25 years ago, roughly, is that we knew that a counterexample more than 25 years ago, in 1986, we knew that a counterexample to Fermat would give you a Frey curve that could not be associated to a modular form. And if we somehow knew that this Frey curve were modular, then we'd get a contradiction. So that was what we had many years ago in 1986. And then Taylor, Wiles, and Wiles came along and they proved that semi-stable elliptic curves are modular, and that completed the contradiction. We showed that this elliptic curve could not have been written down with the properties that we ascribe to it. And now another tiny break from the technicalities is that when the proof was written up, there was a conference at Boston University organized by Gary Cornell, Joe Silverman, and Glenn Stevens. Two of the organizers are here at this conference. And all of the people associated with the proof explained their parts of their contributions at a conference that was quite long in the summer of 1995 at Boston University. And now, what I could try to do is to tell you from the point of view of 1994 how Taylor, Wiles, and Wiles proved that the elliptic curve was modular. But what I'd like to do is kind of go through these slides very, very quickly and just give you some of the highlights. So one of the highlights is that you have to have a modular form coming from somewhere in their way of doing it. And what they did was they said, even though we're interested in the mod P representation attached to this elliptic curve, we're going to start with a mod 3 representation, which we know a lot about. And we know a lot about the mod 3 representation because the image of it is inside of a group that's so small that the image has to be solvable. And using the work that had been published not too long before by Langlands in his very long book, Base Change for GL2, using that plus an extra contribution of Jerry Tunnell, you could actually prove that the mod 3 representation was modular. And here's a photo of Jerry Tunnell that I took at the Abel Symposium in Minnesota in honor of John Tate, our common advisor. And what Taylor and Wiles do is they say, knowing initially that the mod 3 representation is modular, we're going to go up powers of 3 and prove that the mod 9 and mod 27 and mod 81 representations are all modular. And they do this by a new technique that they introduced using the deformation theory of Barry Mazur, and they actually get that the entire package of mod 3 to the n representations are all modular. And technically, you can say, you can use the language of Andre Weil and John Tate. You can say that they proved that the three-adic representation was modular because all of the three-power representations are modular. And here's another photo. This is right after Wiles's announcement. Don't want to dwell too much on the photos because there isn't a lot of time left. But the whole point is that what they proved is called a modularity lifting theorem. And that starts with a modularity of a mod 3 representation, or it could be a mod L representation, but they take L equal 3 because that's what they had, and they deduce the modularity of an entire package. And technically, what they do is they use some techniques of commutative algebra, plus many, many more techniques that they introduced for this purpose, to prove the isomorphism of two rings. So one of them is a universal deformation ring that's called script R, and one of them is just the Hecke ring associated in the situation, which is a ring associated to those representations that are associated with modular forms, and they proved an R equal T theorem. And so the proof that they gave, as presented in 1995, involved a number of components. So one of the components was my level lowering from 1986. Another was the theorem of Langlands and Jerry Tunnell that started things with the modular form. And the new contribution was this R equal T theorem, the modularity lifting to get that the elliptic curve was modular. And there's another little image at the bottom of the slide. It's the handwriting of Andrew Wiles, who wrote to me in the 1980s, "I trust that you are busy preparing your demonstration of Fermat's last theorem." It's on a postcard that he sent me, and I did not make this up. And I don't have time to talk to you about the deformations, but I do want to say that they proved in the end that some natural ring homomorphism, which a priori is surjective, in fact is an isomorphism. And they proved R equal T in this way. And what they did is they launched an entire subject. So Mark Keeson, who many of you know, professor at Harvard, was one of the first to prove many more R equal T theorems with varying hypotheses in different contexts. And in preparation for this lecture, I consulted a number of people who I thought were more expert than I am. One is Frank Caligari from Chicago, who said that in looking only at the very top tier journals, and he has high standards, he could find at least 25 articles where the main result is an R equal T theorem. And he has a blog called Persiflage. And so one thing that happened beyond 1995 was this kind of whole fluidity of proving R equal T. And another, which is maybe not as widely appreciated, is an article that Richard Taylor wrote around 2000. He spoke at the ICM in 2002, I believe. And the article is Remarks on a Conjecture of Fontaine and Mazur. And what he did was he introduced an entirely new tool called potential modularity, where you start with something that you want to prove to be associated with modular forms, and you maybe can't do it, but if you make a small extension from the ground field of rational numbers to a finite extension that you can make totally real, then you can get the thing to be modular, and it will be associated with Hilbert modular forms. And this tool, plus all these R equal T theorems, enabled Shekhar and Jean-Pierre Vinton-Berger to prove in 2008 the whole conjecture that Serre had proved in, that Serre had published as a conjecture in 1987. And as you must have inferred from what I said, if you knew Serre's conjecture, then this contradiction would just come immediately. You wouldn't need my level lowering. And so in doing so, even just formally, they simplified the proof. although they used a lot of the tools that were then reigning, including, I believe, my techniques, certainly the techniques of Taylor, and certainly all these R equal T theorems. So I'm out of time. I just want to give you kind of an executive summary of the rest, which is that now all of the people who really work in the subject are so familiar with the tools that if you try to ask them how to prove modularity, how to prove Fermat's last theorem, as Michael Harris said in an article in Quantum magazine, 10 different young people will tell you 10 different proofs. There are already kind of enough pieces on the chessboard to checkmate the king in lots of different ways. So the proof of Fermat's last theorem has changed in the sense that it's gotten much, much richer, and there are lots of ways to do it. And whether or not you want to say this is a new proof or a different proof really depends on your perspective. But I think one of the objectives in the subject was to reduce the reliance on my techniques, which a lot of people didn't really study when they were studying the R equal T theorems, and also the reliance on the Langland's results that really were analysis more than algebra. And so it's kind of up in the air whether you consider that there's a new proof or a different proof or a modified proof. The final thing that I want to say with just 2 photographs is that, in case you were wondering, I really did enjoy being president of the American Math Society for 2 years, just as many of my colleagues, Jill, seems to be enjoying her presidency, and her successor, Ruth Charney, I'm sure will enjoy being president. And I just have 2 photos that I want to conclude with. One was a photo that was taken at the 2012 JMM at the Springer booth, where the members of the nominating committee asked me whether I would run for president, or asked me whether I would run for council, and I agreed to run for council. So I've been to many council meetings. My last council meeting was Tuesday of this week. It has been an honor and a pleasure to be the president of the American Math Society.
Thank you. Thank you, Ken. That was a beautiful lecture. I'm afraid there's no time for questions as we get ready for the prize session, but please join me in thanking Ken again.